Welcome to the Deep Dive. We're the show that, slices through complex stuff, pulls out the important bits, and hopefully gives you those aha moments.
That's the goal.
And today, we're not just diving deep, we're doing like a full forensic exam
Yeah.
on the absolute heart of modern life, the engine.
Mm-hmm. The powerhouse.
Seriously, think about it. That quiet hum on your commute or, the roar taking you on a road trip. Your car's engine is kind of the unsung hero. It's this incredibly complex dance of metal, fire, precision.
It really is an amazing piece of engineering.
But when that dance stumbles, when it grumbles instead of purrs, or worst case, just won't start.
Yeah, that's when the frustration kicks in
Yeah,
and the mystery begins.
absolutely. And that mystery, that mechanical detective work, that's what we're unraveling today.
We're going deep into engine repair, specifically looking through the lens of the ASE A1 engine repair certification.
Right. And this isn't just about, turning wrenches. It's about truly understanding these intricate systems, these combustion engines that power everything.
And learning how skilled techs diagnose really complex issues. It's a process.
So for sources today, we've got some fascinating stuff. Primarily, it's a self-study guide for that ASE A1 cert for motor age training.
Which is basically a gold mine of practical know-how for technicians, whether they're just starting out or already experienced.
Yeah, and we've also got some extra material on diagnostic tools, like from Bosch, just to see how the theory meets, the real-world tech.
Right, the tools they actually use day to day.
So our mission for you today, we want to unpack all this info, pull out the most important nuggets, and give you a real shortcut to understanding what it means to be well-informed about engine repair.
Whether you're just curious about what's under your own hood, maybe thinking about a career, or honestly, if you just love a good mechanical puzzle.
Exactly. If you love figuring things out, this is for you. Let's get started.
All right. So to really get a handle on engine repair, we kind of need to understand the world it lives in first, the professional landscape.
Which brings us to ASE, right?
Hmm.
The National Institute for Automotive Service Excellence.
That's the one. ASE. You see those blue and white logos everywhere.
So break it down for us. What is ASE, and why should, the average car owner even care?
Okay, so ASE is a nonprofit, been around since 1972. And their whole reason for being is to improve the quality of car service and repair, period.
So like a standards body
Yeah,
setting the bar.
Exactly. Think of it as the gold standard, the benchmark for technicians across North America. It's about making sure the person working on your car actually knows what they're doing. They've proven it.
Okay, that makes sense. And their reach is pretty huge, isn't it?
Oh, absolutely. It's massive. Right now, there are over 400,000 ASE certified techs out there.
Wow.
Yeah, and they cover something like 40-plus different specialty areas. It's not just engines. It's brakes, electrical steering, suspension,
Yeah.
even, advanced hybrid stuff now. It's really comprehensive.
400,000. That's a lot of certified people. So, okay, for the technician, what does having that ASE certification actually do for them, and what does it mean for me, the customer?
Great question. For the tech, it's like this powerful, independent proof that they know their stuff, both the theory and the practical hands-on experience. It boosts their professionalism, definitely opens doors for career growth,
Better jobs, maybe?
for sure. And maybe most importantly, it builds huge customer confidence. The source material actually points out that over 75% of certified shops employ at least one ASE certified technician.
75%. That's significant.
It really is. It tells you that the shop values competence. So for you, the car owner, seeing that ASE patch on a uniform or a sign on the wall, it's basically instant reassurance. You know you're dealing with someone who's met tough industry-wide standards.
Okay, so it's not just a sticker. It's a real indicator of skill. Got it. Now let's zoom in on the A1 certification, engine repair. That sounds pretty fundamental.
It absolutely is. The A1 is all about the core of the vehicle, the engine itself. It's foundational knowledge for any serious automotive professional.
And the test itself, I hear it's not exactly a walk in the park.
Definitely not. It's multiple choice. But the questions are written by a real mix of experts. You've got working technicians, educators, even engineers from the car manufacturers and tool companies.
So they're relevant questions based on real-world stuff.
Exactly. They're designed to reflect what techs actually face in the shop every day, not just textbook theory.
And it's not just simple A, B, C, D, pick one, is it? There are different styles of questions.
That's right. They mix it up to really test critical thinking. You've got your basic direct or completion. Find the single best answer. Then there are most likely questions.
Okay, what are those?
They give you a scenario and several plausible answers, but you have to pick the one that's, well, most likely or the most correct based on the info given. It requires judgment.
Makes sense. Prioritizing possibilities.
Exactly. But the ones that really make you think are the Technician A and Technician B questions.
Ah, I've heard about those. They sound like mini puzzles.
They kind of are. You get a situation, maybe a diagnostic problem. Then Technician A says something about it and Technician B says something else.
And you have to figure out who's right, or if both are right, or wrong.
Precisely. You evaluate each statement on its own. Is A right? Is B right? Both. Neither. It forces you to really dissect the information and apply your knowledge.
Can you give us an example? Like, how would that work?
Sure. Let's say an engine's overheating. Technician A says a stuck-open thermostat could cause this. Technician B says a clogged radiator could cause this.
Okay.
Well, you need to know that a thermostat stuck open actually makes an engine run too cool, not overheat. So Technician A is wrong.
Right.
But a clogged radiator, that absolutely would restrict coolant flow and cause overheating. So Technician B is correct.
So the answer would be Technician B is correct.
Exactly. See, it's not just recalling facts, it's understanding the consequences of those facts in a practical situation.
That really tests understanding, not just memorization. What about the acceptee questions? Those sound tricky.
They keep you on your toes. They'll list several correct statements or components related to a system, and you have to identify the one that doesn't belong or is incorrect. It forces you to know all the aspects of the topic, not just one right answer.
Okay, so you passed this tough test. You're certified, is that it? Good for life?
Nope. And that's actually a really important point. You have to recertify every 5 years.
Every 5 years. Why so often?
Because automotive technology changes fast. Think about cars from 5 years ago versus today. New systems, new materials, new diagnostic approaches. Recertification ensures that ASE techs stay current. They have to keep learning.
That makes a lot of sense. Things definitely don't stay the same under the hood.
Not at all. And the testing process itself has evolved too. It's mostly computer-based testing, or CBT, now.
What are the advantages of that?
Flexibility is a big one. You can schedule tests pretty much year-round at different centers. And a huge plus for the techs. You get your unofficial score right after you finish.
Instant feedback. That must reduce some anxiety.
Definitely. Most regular tests are timed, maybe 30, 45 minutes. Some of the really advanced ones, like the L1 or L2 tests, can be up to 2 hours, though.
And if you don't pass?
There's usually a short waiting period, like 2 weeks, before you can retest. Gives you a chance to brush up.
And that study guide we mentioned, the Motor Age one, that's designed specifically to help with this whole process.
Exactly. Guides like that are crucial. They break down the content areas, explain the question types we just talked about, and give you lots of practice questions so you know what to expect and can walk in feeling prepared.
So this whole system, the rigorous testing, the recertification, the study guides, it all feeds into making sure these techs are really capable.
And capable of using the tools of the trade. Which brings us to the modern diagnostic equipment. Our source mentioned Bosch, for instance.
Yeah, the tools today are incredible. We're talking way beyond just wrenches. These are sophisticated diagnostic machines.
Like scan tools with OE-level coverage.
Exactly. OE level means they have the same diagnostic power as the tools the car manufacturers themselves use. They don't just read codes. They show live data what every sensor is doing in real time.
And bidirectional functions, what's that?
That means the tool can talk back to the car. It can command components to activate run-specific system tests. It's not just passive reading, it's active testing.
Wow. And it's not just for cars, right? Bosch has stuff for bigger vehicles, too.
Yep. Heavy-duty diagnostics for trucks and buses. And a huge area now is ADAS recalibration.
ADAS. Advanced Driver Assistance Systems, like lane assist and adaptive cruise.
Exactly. After certain repairs, like a windshield replacement or suspension work, those systems need to be precisely recalibrated to work correctly. These tools handle that.
And then tools for just testing electrical and mechanical systems.
Right. Oscilloscopes to see electrical signals, specialized testers. It's a whole arsenal.
So it's really fascinating, and maybe the key takeaway here for you listening is how ASE certification connects to all this tech. It ensures the technician doesn't just know how to plug in the fancy scanner, but they understand why the scanner is showing what it's showing.
Ah, the meaning behind the data.
Precisely. Getting a trouble code is one thing. Knowing what systems that code relates to, what other tests to run, how to interpret the live data to find the root cause, That's the real skill.
It's the difference between just reading a code and actually diagnosing the problem, being a true automotive detective.
Exactly. It's that deep diagnostic understanding.
Yeah.
And that leads us perfectly into our next part, the actual detective work of general engine diagnosis.
Yes. This is where the rubber meets the road, so to speak.
Yeah.
When a car acts up, it rarely just tells you what's wrong.
No, it gives you symptoms, clues.
Mm.
And like any good detective, the technician needs a systematic approach. You can't just guess.
Trial and error gets expensive fast.
And frustrating. It's about methodically ruling things out to zero in on the real culprit. It really is like being a mechanical Sherlock Holmes.
So diagnosis starts when? The moment the check engine light comes on.
Or even before that. The moment the car shows any problem, a weird noise, rough running, won't start. That's when the investigation begins.
And the first step is gathering intel.
Absolutely. Yeah. Listen carefully to the customer. When does it happen? What does it feel like? Then check for stored diagnostic trouble codes. Absolutely. But also, critically, look up technical service bulletins, or TSBs.
TSBs, what are those?
They're like memos from the car manufacturer about known issues or common problems with specific models, and often the recommended fix. Why reinvent the wheel if there's a known pattern?
Smart. Leverage the collective knowledge. Okay, let's talk common complaints. The big one. No start, no crank. What does that mean and where do you even start?
Okay, no start, no crank usually means either you turn the key and nothing. Silence, no engine rotation at all. Or the engine cranks, you hear it turning over, but it just won't fire up and run.
Two different scenarios. So, for the no crank, the silence, where do you look first?
Battery, battery, battery. Always start there. Check the voltage should be about 12.6 volts fully charged. Then do a load test. That tells you that the battery can actually deliver the power needed to crank the engine.
It might show good voltage, but collapse under load.
Exactly. Then you do a starter draw test to see how much current the starter itself is pulling. And of course, check the simple stuff. Battery cables clean and tight. Any corrosion, check the wiring in the starter circuit.
Makes sense. Cover the basics first. Now, what if it does crank, but just won't start?
Okay, now we're narrowing it down. If it cranks but won't start, you're almost always missing one of the three essential ingredients for combustion: spark, fuel, or compression.
The classic trio. Spark, fuel, compression. How do you figure out which one is missing?
Systematically. For spark, you use a spark tester to see if you're getting spark at the plugs or coils. Check the distributor if it has one. For fuel, you check fuel pressure at the rail. Is it within spec? Is there good volume? Any leaks? Are the injectors actually firing, getting an electrical pulse?
You can test the injector pulse.
Yep. With a tool called a Noid light, or using a scope. And don't forget fuel quality. Bad gas is a real thing.
Okay. And compression.
That requires a compression test. You screw a gauge into the spark plug hole and crank the engine to measure how much pressure each cylinder builds. Low compression points to internal engine problems like worn piston rings or valve issues.
What about timing? Could that cause a crank no start?
Absolutely critical. Even with good spark, fuel, and compression, if the engine's timing is off, it won't run. A timing belt or chain could have jumped a tooth, or there could be issues with valve timing.
And sensors play a role here.
Huge role. The crankshaft and camshaft position sensors tell the engine's computer, the PCM or ECM, exactly where the engine is in its rotation. That computer uses those signals to time the spark and fuel injection perfectly. If those sensors fail or give bad signals, the timing goes haywire. No start.
Okay, moving beyond starting issues. Oil leaks. Annoying, messy. Pretty common, right? Got the usual suspects.
Very common. Often it's just seals and gaskets getting old, hard, and brittle from heat cycles. Valve cover gaskets, oil pan gaskets, crankshaft seals. Another frequent culprit is the oil filter housing itself.
The housing can leak.
Yeah, the source actually mentions that standard oil filter housing kits are specifically designed to fix common leak points on the original factory housings. Sometimes these kits even include new sensors or gaskets needed for the job.
So how do you find the exact source of the leak? Oil gets everywhere.
That's where UV dye comes in handy. You add a fluorescent dye to the engine oil, run the engine for a bit, then shine a black light or UV lamp around. The leaking oil glows brightly, pinpointing the source, even if it's a tiny seep high up on the engine. Turns you into a bit of a forensic investigator.
Cool, like CSI for cars. Okay, what about coolant leaks? Those seem more serious because of overheating potential.
They are definitely serious. Overheating can kill an engine fast, so inspection has to be thorough. Check the radiator, all the hoses, the water pump, intake manifold gaskets, engine block, cylinder head, everywhere coolant flows.
How do you test for leaks if you don't see an obvious drip?
Pressure testing is key. You use a hand pump to pressurize the cooling system up to the spec listed on the radiator cap. If the pressure drops, you know there's a leak somewhere, even if it's small or internal.
What else?
Visual inspection, looking for telltale stains or residue. And sometimes you can smell it. That distinct sweet smell of ethylene glycol means coolant is escaping somewhere.
And overheating is the main symptom, but you said leaks can cause other issues too.
Right. Even a small leak can lower the system's boiling point or cause air pockets, reducing efficiency. That might lead to things like a rough idle or misfires because the engine isn't staying at its optimal temperature even if the gauge doesn't shoot into the red.
Okay, this next category is fascinating. Engine noises? You said a good tech becomes an audio detective. What kinds of sounds are we talking
A
about?
whole range, and each tells a story. You might hear a low thud or a sharp rap that often points to bearing noise. Could be main bearings, rod bearings, maybe wrist pin noise, or even crankshaft end play.
Okay, what else?
A lighter tick or clatter, especially from the top of the engine. That's usually valvetrain noise. Worn rocker arms, lifters, push rods, maybe a stretched timing chain slapping against its guide.
And piston noise.
Often described as piston, slap a duller, hollower sound, sometimes worse when cold, as the piston rocks slightly in the cylinder bore before it heats up and expands. A skilled ear can often tell where the noise is coming from and what kind of component is likely involved just by listening.
What about that knocking or pinging sound people worry about?
That's usually detonation or pre-ignition. They're slightly different, but both are abnormal combustion. Instead of a smooth burn, you get uncontrolled explosive ignition.
What causes that?
Often excessive heat in the combustion chamber, maybe carbon buildup acting like a glow plug, or using fuel with too low an octane rating.
Yeah.
Sounds like rattling, pinging marbles in a can. Like, definitely not good long term.
Any other common noises?
Sure. Hydraulic lifter noise is a common tick, often louder when the engine's cold, caused by too much clearance inside the lister. Spark knock is another term for detonation. Oh, and importantly, some noises are normal. Direct injection engines often have a distinct ticking sound from the high-pressure injectors. You need to know which clicks and ticks are okay and which ones signal trouble.
So, hearing these sounds isn't just an annoyance, it's a diagnostic clue. Okay, let's switch from sound to sight. Exhaust smoke. What can the color tell you?
A surprising amount. It's a great visual diagnostic. Black smoke. That almost always means a rich fuel mixture. Too much fuel, not enough air.
Like what?
Could be a clogged air filter, a faulty fuel pressure regulator, leaky injectors, maybe a bad sensor telling the computer to dump extra fuel.
Okay. What about white smoke?
White smoke, especially if it smells sweet, is bad news. That's usually coolant burning in the combustion chamber.
How does coolant get in there?
Typically a blown head gasket, a cracked cylinder head, or even a cracked engine block. It's a serious internal leak.
Not good. And the third color? Blue or gray smoke?
That's the classic sign of burning oil.
Meaning oil is getting into the combustion chamber somehow.
Exactly. The most common causes are worn piston rings that aren't sealing the cylinder properly, or worn valve guides or valve stem seals, allowing oil to leak down past the valves. Sometimes PCV system problems can also cause it by increasing crankcase pressure.
PCV. What's that?
Positive crankcase ventilation, we'll touch on that more later, but basically if it's clogged, pressure builds up and can push oil past seals. First step, though, is usually check the dipstick. Is the oil level dropping excessively? Blue smoke confirms where it's going.
So color is a huge clue. Black, white, blue, gray. Each points in a different direction.
A very direct visual cue.
Okay, so we've got noises, smoke signals. How do techs systematically test the engine's internal health beyond just observation?
That's where specific diagnostic tests come in. Engine vacuum testing is a really powerful, old school but still relevant test.
How does that work?
You connect a vacuum gauge to a port on the intake manifold. A healthy engine running at idle should pull a steady vacuum, typically somewhere between 17 and 22 inches of mercury, depending on altitude.
And if it's not steady and normal, what can the gauge tell you?
Oh, a lot. The way the needle behaves is key. Is it steady but low? Maybe late timing or uniformly low compression? Does the needle fluctuate intermittently? Could be a sticking valve or a regular ignition miss.
What else?
Does it drop regularly, like rhythmic dips? Often points to a burnt valve leaking compression on one cylinder. Is the needle fluctuating wildly, maybe getting worse as RPMs increase? Could be weak valve springs or worn valve guides.
Wow.
Does the vacuum drop gradually when you rev the engine and hold it? That often signals a restricted exhaust, maybe a clogged catalytic converter. Each pattern is like a signature for a specific type of internal problem.
It really is like reading the engine's vital signs. What other tests measure internal health?
Well, there's the cylinder balance test. This helps figure out if all cylinders are contributing equally to the engine's power. It's great for pinpointing misfires or identifying a weak cylinder,
How does that work?
usually done with a scan tool nowadays. It momentarily disables fuel or stark to each cylinder one by one and measures the resulting drop in engine speed. A cylinder that causes less of a drop is the weak one.
Clever. And then the compression test we mentioned earlier for crank no start.
Absolutely fundamental. It directly measures each cylinder's ability to seal and build pressure.
Remind us how the dry versus wet test works again.
Sure, you do a dry test first, measure the compression. If a cylinder is low, you add a little squirt of oil into that cylinder. That's the wet test. Crank it again. If the compression reading jumps up significantly,
The oil temporarily sealed the rings.
exactly, points strongly towards worn piston rings. If the compression stays low or only comes up a tiny bit.
The problem is likely valves or the head gasket because oil won't seal those.
Precisely. It's a great way to differentiate between bottom-end rings and top-end valves gasket compression loss.
Okay, but what if you need to know exactly where that compression is going? Is it the intake valve, exhaust valve, rings, or gasket?
Now you're talking about the ultimate leak finder, the cylinder leakage test, sometimes called a leak down test.
How does that one work?
You bring the cylinder to top dead center, TDC, on its compression stroke, so both valves should be closed. Then, instead of measuring pressure build, you pump compressed air into the cylinder through the spark plug hole.
And then you listen.
Exactly. You listen for where that air is escaping. Air hissing out the tailpipe,
That exhaust valve.
hissing out the throttle body or air intake,
That intake valve.
bubbling sound in the radiator.
Head gasket leak into the cooling system, or maybe a crack.
And if you hear air rushing out of the oil filler cap or the dipstick tube,
Worn piston rings leaking into the crankcase.
bingo. The leakage test pinpoints the exact source of the compression loss.
It really feels like putting all these pieces together, the noises, the smoke, the vacuum readings, the compression and leakage tests. That's what creates the full picture.
That's exactly it. It's rarely just one thing. It's combining all the evidence, using a systematic process of elimination to arrive at the correct diagnosis.
Yeah.
That methodical approach is the skill.
And often, that diagnosis points towards needing work on the top part of the engine.
Very often. Which takes us into the cylinder head and valvetrain, the top end.
Okay, the top end. That seems like delicate territory. How does a tech even start taking apart the cylinder head?
Very carefully and systematically.
Huh.
First, you have to disconnect everything attached, cooling hoses, exhaust manifold, fuel lines, wiring harnesses. Then, depending on the engine design.
OHV versus OHC.
Right, on an older overhead valve OHV engine, you'll remove things like rocker arms and push rods first. On a modern overhead cam OHC engine, you're dealing with timing belts or chains connected to the camshafts on the head itself. That all has to be carefully disassembled.
And the head bolts, I remember you said they're special.
They really are.
Yeah.
They have to be loosened in a specific sequence, usually the reverse of the tightening sequence, and often in stages. This prevents warping the head as the clamping force is released.
And some bolts can't be reused.
Correct. Those are torque-to-yield TTY bolts. They're designed to stretch permanently when first tightened to get a very precise clamping force. Once stretched, they're done. Reusing them is asking for trouble, like a blown head gasket down the road. Always replace TTY bolts,
Good tip. What about core plugs?
sometimes called freeze plugs. Technicians might remove those from the head to allow for better cleaning and inspection of the internal coolant passages.
Okay, heads off, bolts are handled. Now, inspection, cleaning first.
Absolutely paramount. Got to get rid of all the carbon oil, gasket residue, might involve bead blasting, chemical dips, hot tanks. You can't properly inspect or measure a dirty head.
Makes sense. So once it's clean, what's the biggest concern? Cracks.
Cracks are definitely a major concern, usually caused by thermal stress overheating, then cooling too quickly. Common spots are around valve seats, spark plug holes, exhaust ports.
How do you find them if they're tiny?
Several ways. Careful visual inspection, obviously, but also dye penetrant testing, where a colored or fluorescent dye seeps into cracks, making them visible. For iron heads, magnetic particle inspection works well. And pressure testing the coolant passages is definitive pump air or water pressure into the jackets and see if it holds or leaks out through a crack.
Okay, besides cracks, what about warpage? Can the head actually bend from heat?
Oh yeah, warpage is very common. The mating surface, where it bolts to the block, needs to be perfectly flat. Heat, or even improper tightening can cause it to warp.
How flat's flat?
We're talking incredibly precise. You check it with a precision straight edge and field gauges. Specs are often just a few thousandths of an inch, maybe 0.001 to 0.004 max tolerance across the whole surface.
Wow, what if it's warped more than that?
It has to be resurfaced, milled or ground perfectly flat again. And if you remove material, you have to account for that, maybe with a thicker head gasket, to maintain the correct compression ratio and valvetrain geometry.
So much precision. Okay, what about the valves themselves and the guides they slide in?
Valves take a beating. You inspect the stems for wear or damage, the faces for pitting or burning, the keeper grooves. As for the valve guides, their job is critical. They guide the valve and help transfer heat away from it.
What happens if the guides wear out?
You get excessive stem-to-guide clearance. This lets oil sneak past into the combustion chamber, causing oil consumption and blue smoke. It hurts vacuum, leads to carbon buildup, and because heat transfer is reduced, the valve itself can overheat and burn.
How do you measure that clearance?
With precision tools, like a dial indicator on the valve stem or a small hole gauge and micrometer, if the clearance is too much, the guides need repair or replacement. Options include knurling, displacing metal to tighten the bore, reaming for oversized valve stems, or pressing in new guides, often made of bronze or cast iron.
And the valve seats, where the valve actually seals.
Also critical. The seat needs to be perfectly round, concentric with the guide, and have the correct angle, usually 45 degrees, and width, typically very narrow, like 164 to 132 too. You look for wear, pitting, cracks. If damaged, the seats are refaced using special grinding stones or cutters. A good valve job ensures a perfect seal between the valve face and seat.
It's like every single surface has to be perfect. What about the springs? They're under constant stress.
Huge stress. You inspect springs for cracks, rust, signs of overheating, bluish color. But you also test them, check their free height, check if they're square, not leaning, and most importantly, test their pressure at installed height using a spring tester. Weak springs can lead to valve float at high RPM, where the valve doesn't close fast enough, causing power loss and potential engine damage.
Do you use shims sometimes?
Yes, if the installed height is slightly off, precise shims can be placed under the spring to achieve the correct tension.
Okay, let's move to the camshaft and the rest of the parts that operate the valves. What gets checked there?
The camshaft lobes are key. You measure the lobe lift using a dial indicator to see how much they actually push the valves open. Compare that to specs. Excessive wear here means valves won't open fully.
What else on the cam?
Check camshaft end play, front to back movement, and run out, checking if it's bent, also using a dial indicator. Then the timing chain or belt and sprockets. Look for wear on teeth, stretched chain belt, damaged guides or tensioners. Chain stretch can also be measured. And of course, timing mark alignment during assembly is absolutely critical.
What about the lifters, the parts that ride on the cam lobes?
Hydraulic lifters are common. They use oil pressure to maintain zero valve lash automatically. You check them for being collapsed, meaning they aren't holding oil pressure properly, which causes noise. There are specific leak-down testers for this. Solid lifters require periodic adjustment. Roller lifters, common now, need their rollers and axles inspected for wear.
And rocker arms, push rods.
Inspect rocker arms for wear at the pivot point and where they contact the valve stem or push rod. Check push rods on OHV engines to make sure they aren't bent or worn at the ends. Everything in the valvetrain chain needs to be checked.
Okay, so after all that meticulous inspection and repair, it's time to put the head back on, just as precise as taking it off.
Even more so, maybe. Cleanliness is absolute. Mating surfaces spotless. Always use a new head gasket. Multi-layer steel. MLS gaskets are common now, very robust.
And the bolts.
Follow the manufacturer's torque sequence and stages religiously. Use a calibrated torque wrench. Often involve multiple torque steps plus specific angle turns. And remember, if they're TTY bolts, use new ones. No shortcuts here.
And finally, adjusting the valves.
If it's an engine with adjustable valves, like solid lifters, you set the valve lash clearance precisely according to spec, usually with the engine cold or hot, depending on the procedure. For hydraulic lifters, you typically adjust them to zero lash, then maybe a slight preload, allowing the lifter to do its job automatically. Getting the head installation and valvetrain set up perfect is absolutely crucial for performance, efficiency, and longevity.
The level of detail is just incredible. It really highlights the skill involved. Now let's go deeper, right down to the foundation.
Yeah.
The engine block.
Right. The block is the literal core. Disassembly needs to be just as organized as the head. Remove external parts, then internals like the crank, pistons, rods. Keep everything labeled, bagged, organized. You need to know exactly which part came from where for inspection and reassembly.
And cleaning the block, I bet that's a big job.
Huge. And critical. Chemical dipping, hot tanks, shot blasting, whatever it takes to get it perfectly clean inside and out. Oil passages, coolant jackets, cylinder bores, everything has to be spotless. Any leftover grit or sludge is a recipe for disaster during reassembly.
Okay, clean block. What are the main inspection points here? Still looking for cracks.
Definitely. Cracks are a major concern to the block, too. Check around freeze plugs, main bearing bores, the saddles for the crankshaft, lifter bores, deck surface, cylinder walls. Again, dye penetrant or magnetic particle inspection might be needed to find hidden cracks.
And the deck surface, where the head bolts on.
Just like the head, the block deck needs to be perfectly flat. Check for warpage with a straight edge. If it's warped, it needs machining, resurfacing. And again, you have to factor in any material removed.
What about the cylinder bores, where the pistons live? That seems like a high wear area.
Extremely high wear. You look for a wear ridge at the top where the rings stop. Look for scoring or scratches on the walls. And you measure carefully.
Measure what?
Taper is the bore wider at the top than the bottom. And out of roundness, is it still a perfect circle? You use a precision bore gauge or inside micrometer, measuring top, middle, bottom, and in two directions, thrust and non-thrust sides.
And if they're worn beyond limits?
Options are honing to restore the surface finish, that critical crosshatch pattern that holds oil, if wear is minimal. Boring the cylinders oversized to fit larger pistons if wear is significant. Or in some cases, installing cylinder sleeves or liners.
Okay, moving down. Main bearings and the crankshaft. Huge parts. What's checked there?
The main bearings are inspected visually for scoring, pitting, fatigue, signs of oil starvation. But the critical measurement is oil clearance.
How do you measure that tiny gap?
Using plastic gauge. It's a thin strip of crushable plastic. You lay it across the bearing journal, install the bearing cap, and torque to spec, then remove the cap. The plastic strip gets flattened. You measure its width against a scale provided, and that tells you the exact clearance, usually down to thousandths of an inch.
That's clever. And the crankshaft itself?
The journals, the smooth surfaces where the bearings ride are measured for size, taper, and out of roundness using micrometers. You also check the crank for straightness, runout, by mounting it on V-blocks and using a dial indicator. Any significant wear, scoring, or bending might mean the crank needs grinding undersize or replacement.
What about the parts doing the pushing? Pistons and connecting rods?
Pistons get inspected for cracks, especially around the pin boss. Scoring on the skirts, signs of burning on the top from detonation, wear in the pin bore, and wear in the ring grooves. You measure the piston diameter too.
And the rings?
Check the piston rings themselves for wear, but also check the ring groove clearance, how much up and down slop the ring has in the groove, and the ring end gap, the gap between the ends when the ring is installed in the cylinder. Both are critical for proper sealing.
Connecting rods?
Inspect connecting rods for bending or twisting. Check the MIG end bore, where it bolts to the crank, for size and roundness. Check the small end bushing, where the piston pin goes, for wear. Like everything else, precision measurements are key.
Okay, after all this inspecting, measuring, machining, cleaning, it's finally time for engine assembly. The moment of truth.
It really is. And absolute precision is non-negotiable here. Everything must be spotlessly clean. Everything needs proper assembly lubricant. Use the right lubes on bearings, cylinder walls, bolts.
And torque wrenches are mandatory.
Absolutely. Every critical fastener, main caps, rod bolts, head bolts, flywheel bolts, has a specific torque value and often a tightening sequence. Follow it exactly. Use a calibrated torque wrench. And again, remember those TTY bolts, new ones only.
How do you get the pistons with their rings into the cylinders without breaking anything?
Carefully. First, make sure the piston is facing the right way, often marked front. Install the rings correctly, making sure the gaps are staggered around the piston, not lined up. Then, use a piston ring compressor tool to gently squeeze the rings down so the piston assembly can slide smoothly into the cylinder bore. Tap it in gently with a hammer handle.
And installing the crank and cam.
Proper bearing placement is key. Make sure oil holes line up. Install thrust bearings correctly to control crankshaft end play. Install timing components, ensuring all timing marks line up perfectly. Check crank and cam end play with a dial indicator once installed.
Gaskets and seals.
Always new.
Yeah.
Never reuse old gaskets or seals. Clean meeting surfaces meticulously. Use sealant only where specified by the manufacturer. Modern MLS multi-layer steel gaskets are common and very effective, but require very clean, smooth surfaces. The attention to detail here It's what makes the difference between an engine that lasts 100 miles and one that lasts 100,000 miles.
It's like performing surgery. Incredible precision. So mechanical assembly is done, but the engine needs its lift support systems, right? Lubrication and cooling.
Absolutely vital. Let's start with the lubrication system. The engine oil itself is critical. Use the correct viscosity, like 5W30, an API classification recommended by the manufacturer, and regular oil changes, not optional. They remove contaminants and keep the oil doing its job.
What actually moves the oil? The oil pump.
Yep. Usually a gear or rotor-type pump down in the oil pan. It creates the pressure. Technicians check oil pressure with a gauge to make sure it's within spec. Low pressure is a killer. Could be a worn pump, clogged pickup screen, stuck pressure relief valve. High pressure can also cause issues.
Some engines have an oil cooler.
Yes, especially higher performance or heavy-duty engines. It helps keep the oil temperature down. You inspect it for leaks or damage, just like a radiator.
And finding leaks. Still the UV dye trick.
Still the best way for finding elusive leaks. Dye in, run it, black light out. Works like a charm.
Okay, on to the cooling system. Keeping that engine from melting down, what about the coolant itself?
It's not just antifreeze. It's a specific mixture, usually ethylene glycol and water, plus corrosion inhibitors. Using the right type is crucial. OAT, HOAT, hybrid. They have different chemistries. Mixing types can cause big problems like sludge or corrosion. Check the owner's manual. Color isn't always a reliable indicator anymore.
How do techs inspect the cooling system thoroughly?
Check everything. Hoses for softness, swelling, cracks, clamps for tightness, radiator for leaks, bent fins, blockages, internal or external, water pump for leaks or noisy bearings, heater core connections, everything.
And pressure testing is standard.
Standard procedure. Pump it up, see if it holds pressure. Also test the radiator cap. It's designed to hold a specific pressure and also allow vacuum relief when cooling down. A bad cap can cause boiling over or collapsed hoses.
What about the parts driven by belts? Drive belts, pulleys, tensionals.
Crucial. Inspect belts for cracks, fraying, glazing. Check tension too loose, it slips. Too tight, it damages bearings. Check pulleys for alignment and damage. Many cars have automatic belt tensioners now. Check that they're working correctly and providing steady tension.
The thermostat, small part, big job.
Huge job. It controls the engine operating temperature. Test it by heating it in water to see if it opens at the correct temperature. If it's stuck open, the engine runs too cold. Stuck closed, overheats fast. Make sure it's installed in the right direction with a good gasket.
Water pump. What goes wrong there?
Usually leaks from the shaft seal. Look for trips from the weep hole or bearing failure. Noise. It's the heart of the cooling system, circulating the coolant. Replacement requires care with gaskets and torque.
And the radiator itself.
Check for leaks, obviously, but also make sure the fins are clean and straight for good airflow. Bugs, leaves, dirt can clog it up externally. Internal clogs can happen too, from corrosion or bad coolant.
Cooling fans, mechanical or electric?
Both exist. Mechanical fans often have a clutch that engages when hot. Check if it locks up properly. Electric fans need their motors, wiring, relays, fuses, and temperature sensors checked. A fan not coming on is a very common cause of overheating, especially in traffic.
And after any cooling system repair, flushing and bleeding are key.
Absolutely essential. Flush out all the old stuff. Then, after refilling, you must properly bleed all the air out of the system. Air pockets can cause hot spots and prevent proper circulation, leading to overheating even with a brand new radiator or water pump.
Okay, so we have a mechanically sound engine with good lubrication and cooling, but it still needs the supporting cast, right? Fuel, electrical, ignition, and exhaust.
Couldn't run without them. Let's start with fuel and air induction. Basic inspection. Check fuel lines and hoses for leaks or damage. Check the mass airflow, MAF, sensor. It tells the computer how much air is coming in, critical for fuel mixture. Check the air filter. A dirty one restricts airflow.
What about that PCV system you mentioned, positive crankcase ventilation?
Right. Its job is to suck nasty blow-by gases, unburnt fuel, moisture, out of the crankcase and feed them back into the engine to be burned. If the PCV valve or hoses get clogged, pressure builds up inside the engine.
And that causes?
Oil leaks are a big one, sludge buildup, or idle. It's a simple system, but important to keep functional. Just inspect the valve and hoses.
What about engines with superchargers or turbochargers? Power adders.
Forced induction. They cram more air into the engine. Inspection involves checking for air leaks in the plumbing, oil leaks from the turbo supercharger seals, listening for weird noises, whining, grinding, and checking the shaft play on turbos. Also check the wastegate on turbos, or bypass valve on superchargers that controls the boost pressure.
Moving to the other end, the exhaust system, what matters there?
Main components are the manifold, pipes, muffler, and catalytic converter. You're looking for leaks, physical damage, and restrictions.
Leaks are bad because...
Noise, obviously,
I'm correct.
but mainly the risk of carbon monoxide getting into the car. Very dangerous.
And restrictions, like a clogged catalytic converter.
Yeah, that's a common one. If the catalyst inside breaks down or gets clogged, often from an engine running too rich, it chokes the engine, causes major power loss, poor fuel economy, and can even make the engine overheat.
Okay, let's switch to electrical, starting with the battery.
The foundation. Visual check first. Cracks, leaks, corrosion on terminals. Check electrolyte level if it's a serviceable type. Then, testing.
Voltage and...
Check state of charge with voltage, 12.6 V, fully charged, or a hydrometer. Specific gravity 1.260 or 1.280. But the real test is a load test to check its CCA, cold cranking amps, capability. Can it actually deliver the power needed to start the engine?
If the battery checks out but the car won't crank, then you look at the starter system.
Exactly. Check power getting to the starter solenoid and motor. Perform voltage drop tests on the positive and negative cables to find hidden resistance from corrosion or bad connections. Listen to the starter. Does it spin but not engage?
What would cause that?
Could be a bad starter drive, the gear that pops out, or damaged teeth on the engine's flywheel or flex plate. Also need to ensure the starter disengages properly once the engine starts.
And finally, the ignition system, providing the spark.
Crucial. Modern diagnostics rely heavily on scan tools here, checking for misfire codes, looking at live data related to coils and timing. But visual inspection is still important. Check wiring, coils, plug wires if equipped, distributor component for cracks, carbon tracks, oil intrusion.
And the spark plugs themselves.
Pull them out and read them. Look for wear on the electrodes, fouling, carbon, oil coolant. Check the gap. The condition of the spark plugs tells you a lot about the health of the combustion chamber.
What about ignition timing and this variable valve timing, VVT thing?
Ignition timing is when the spark plug fires relative to the piston position. It has to be precise. It's checked and sometimes adjusted. Variable valve timing, VVT, is more advanced. It allows the engine computer to change when the valves open and close on the fly.
Why do that?
It optimizes engine breathing for different speeds and loads, improves fuel economy, lowers emissions, boosts performance. It's complex, but very effective. And yes, the source node's VVT is something you'd likely see questions about on the ASE test because it's so common now. All these systems have to work together perfectly.
Wow. We've really dissected the entire engine and its related systems. So for someone listening who's thinking about getting certified, or maybe a tech needing to recertify, how do they actually prep for this A1 test?
Good preparation is everything. The study guides, like the Motor Age one, are invaluable because they break down the test specifications and task list.
Meaning they tell you what's on the test.
Exactly. They show you the content areas covered and, importantly, roughly how many questions come from each area. That helps you focus your study time.
Okay, so for the A1 engine repair test, what's the breakdown? How many questions for each section?
There are 50 questions total on the main A1 certification test. The biggest chunk is general engine diagnosis. That's 15 questions, or 30% of the test. Makes sense, right? Diagnosis is paramount.
Totally. What's next?
Cylinder head and valvetrain gets 10 questions, 20%. The engine block also gets 10 questions, another 20%. Lubrication and cooling systems have 8 questions, 16%. And the fuel, electrical, ignition, and exhaust system section has the remaining 7 questions, 14%.
Knowing those percentages is really helpful for planning study time. Focus on diagnosis, head valvetrain, and block.
Definitely prioritize those, but you need a solid grasp of everything. And remember, the recertification test every 5 years is shorter, it'll be 30 questions, and focuses more on newer tech and updated procedures.
So what's the best strategy for studying, beyond just reading the guide?
Be active. Take notes. Use flashcards. Explain concepts out loud. And critically, take practice tests. Lots of them.
Why are practice tests so important?
They simulate the real thing, help you manage time, get used to the question formats, and most importantly, they show you where your weak spots are. Don't just take the test. Analyze your wrong answers. Why did you get it wrong? Go back and study that area harder.
Makes sense. Any tips for the actual exam day?
Manage your time. Don't get stuck on one question. Read every question very carefully. Look for those keywords like most or except to. Trust your gut. Don't second-guess yourself unless you're sure you misread something.
And you get immediate results with the computer testing.
Usually an unofficial score right away, yes. Official results come later. But even after you pass, it's good to review the questions if possible. Reinforces the learning.
Let's look at a sample question to see how that technician A/B logic works in practice. Here's question 2 from the source. A compression test shows one cylinder is too low. A leakage test on that cylinder shows excessive leakage. During the test, air could be heard coming from the tailpipe. Which of the following could be the cause? A. Broken piston rings. B. Bad head gasket. C. Bad intake valve. D. An exhaust valve not seating.
Okay, classic diagnostic puzzle. Low compression confirmed by leakage test. The key clue is where the air is escaping during the leakage test, the tailpipe.
So, what does air from the tailpipe mean?
It means the air pumped into the cylinder is escaping out through the exhaust system. Which valve opens to the exhaust system?
The exhaust valve.
Exactly. If it were rings, A, you'd hear air in the crankcase. Head gasket, B, probably in the coolant or adjacent cylinder. Intake valve, C, you'd hear it in the intake. Tailpipe means it's leaking past the exhaust valve, so the answer is D, an exhaust valve not seating properly.
See, that connects the test result directly to the faulty component. Let's try one more. Question 6. A vacuum gauge is connected to the intake manifold of an engine running at idle. The pointer on the gauge fluctuates rapidly but steadies as the engine speed is increased. The test results indicate A. Leaking intake manifold gasket, B. Worn valve guides, C. Late ignition timing, D. A weak valve spring.
All right, interpreting the vacuum gauge. The key symptom is rapid fluctuation at idle that steadies with more RPMs.
Okay.
A leaking intake gasket, A, or late timing, C, usually causes a low but relatively steady reading. A weak valve spring, D, typically causes fluctuations that get worse with RPM, not better.
So that leaves
B, worn valve guides. That slight wobble of the valve stem in a worn guide can cause that rapid flutter at idle vacuum, which often smooths out as engine speed and airflow dynamics change. It fits the symptoms perfectly. Again, it's about knowing what each pattern on the gauge signifies.
That really shows the level of interpretive skill needed. It's not just knowing facts, it's applying them.
That's the essence of good diagnostics.
Well, we have certainly taken a deep dive today, from basic diagnosis through inspecting every intricate part of the engine block and head, covering the vital fluid systems and the supporting cast, and seeing how the ASE A1 certification validates all that knowledge.
Hopefully, you listening have a much clearer picture now of the incredible complexity and precision involved in keeping our engines running right.
It really underscores that engine repair is so much more than just mechanical work. It's systematic problem solving, a commitment to ongoing learning, and, yeah, that detective-like curiosity.
It truly is a blend of science, craft, and critical thinking.
So as we wrap up, maybe the final thought for you is, with this deeper understanding of the engine's inner workings and the diagnostic process, what automotive mystery might you be able to make more sense of now?
Maybe it's just appreciating the skill involved next time you get your car serviced. Or perhaps even tackling a small diagnostic puzzle yourself. Food for thought.